Hello and welcome to York Universe, the astronomy and astrophysics radio podcast, written and presented by students, faculty, alumni, and friends of York University. You'll find us now wherever podcasts are distributed. I'll be one of your hosts this evening. I'm Dr. Elena Hyde, and I'm joined by a very special guest tonight, which I will be introducing shortly, Dr. Thomas Morris. We are broadcasting live from the Allan Carswell Observatory, located at York University in Toronto, Ontario, Canada. York Universe broadcasts live every Monday night at 9 p.m. local Toronto time, or ET. That is Tuesday morning at 2 a.m. UT, if that is more your speed. We are broadcasting live on YouTube at York U Observatory in conjunction with the online public viewing run by our amazing observatory team. So check it out there. If you would like to just listen to the audio and podcast, again, you'll find us anywhere podcasts are distributed, including our website and Spotify and all the rest. If you want to navigate to the live show, find out more about the observatory, our free Wednesday night tours, or anything else, you can go to yorku.ca/science/observatory. If you have any questions or comments or ideas for future topics, please send us an email at observe@yorku.ca. You can also connect with us on social media over on Instagram at York U Observatory, PixelFed at Allan Carswell Observatory over on the Fediverse, and Facebook at Allan Carswell Obs. All of our programs, including this one, are free, but if you would like to make a donation or buy our new all ages coloring book, you can see that same website as before, yorku.ca/science/observatory. Our crew will be monitoring the chat room for questions, posting content, and all kinds of other stuff over on YouTube Live. So if you'd like to follow along with that, please feel free. The current weather in Toronto has been really up and down, bouncing all over. But before we get into the skies above, let me go ahead and introduce Dr. Thomas Morris, our guest for this evening. He is joining us over from the UK. He's an astronomer of many hats over many years. He's working as the director of the computing section in the British Astronomical Association. He was also the year editor for the 2026 British Astronomical Association Handbook, which is very fun. And a little bit of a spoiler, he's also my old colleague from Max Planck Institute in Germany, way back in 2006, 20 years. Time flies. Welcome, Thomas. It's great to have you on the show. How are you doing this evening? Are you getting any observing in?
Thank you very much. Thanks, Dr. Elaine Hyde. So I've had a few clear nights here in the UK. It's been a bit mixed. Of course, the UK is renowned for not having great observing weather, but I've been enjoying Jupiter at the opposition sort of since January. It's quite high up for the UK, and I've got a little Celestron 5 Schmidt-Cassegrain that's ideal for observing planets. So enjoying the red spot and the moon events as the Galilean satellites go around the planet. Always nice to watch.
Oh, absolutely. And Jupiter has been just such a joy in the sky recently. If you can get around the clouds, it has been absolutely miserable in Toronto, Ontario, as well. So I feel like we may be having similar weather. Um,
Mm.
but Jupiter has been really wonderful. It's of course a little bit lower in the sky as we go through May with the sun setting. But it's pretty good. And actually, as we go later on into May, we are going to get Jupiter, the Moon, and Venus coming quite close to that setting sun, sort of May 20th or so. So don't look at the sun, but
Lovely.
um, a wonderful target for sure, and not just for any observations, but also for, of course, kind of our topic of the evening of spectra. We have been watching so many interesting things in the sky recently, of course, with Artemis 2 coming back to Earth successfully and the Orion capsule.
Nice,
Um,
nice.
the observatory here has been doing observations photometrically and spectroscopically of satellites, and even we caught the Orion capsule
Oh, nice. Wow.
while it was in space, I might add, just after they left the moon. And there's so many fun things we can do when we expand our observing out past the, shall I say, the usual creating the pretty pictures, which we all love. I thought we could go and discuss a little bit of fun history and maybe look at some of the fun things that have happened with spectra and how they work over time.
Hmm, definitely.
Now, I know you have an interesting starting for a bit of history with the Bohr model. Would you like to get into that a little?
Yeah, yeah, sure. So, yeah, I mean, I've always been interested in space sort of for as long as I can remember, really. I think just the idea of these planets and moons and the Voyager program in the 1980s when I was growing up was just such a amazing journey of exploration and science. And I guess I mean the understanding what the physics and chemistry of these planets out in space. For a long time, people didn't. The common belief was we would never really understand the the objects were far too remote to ever go and carry out measurements. And so the idea of spectroscopy to be able to look at the lines, the emission from the star or planet is it's just to me it's just like magic. And
Absolutely.
so like it was actually in a chemistry class at school that we covered the Bohr model, which obviously is known to be far too simplistic and kind of empirical model for the hydrogen energy levels. But when we went through because I quite enjoyed maths as well and always been into kind of mathematical physics and saw that the equation could actually predict the hydrogen lines in the spectra. And I guess it was like a light bulb moment that suddenly I realized that understanding atomic structure in a laboratory on Earth or like a computer model could could be extended to look at what's out there in space. And I didn't really do any observational spectroscopy. Sort of, I suppose it was at at college, university, and as an undergraduate in the UK. I studied maths and physics as a degree, which was quite theoretical. And sadly, there wasn't a telescope at Warwick University. There is now. Since I left, they built one, um, which is somewhat ironic. But so I learnt the theory behind the spectra, and then sort of bought a small telescope, the C5 Celestron, and went from there really. Sort of got into um, initially using a grating to just to do visual spectroscopy of the bands in cooler stars like Betelgeuse, and then sort of got the hobby has grown, I guess, and just kept increasing in complexity and capability.
Absolutely. Such a fun topic as well.
Hmm, definitely, as you say, because there's so much science really and history that explains all I guess pretty much all types of astronomical objects.
Yeah, and it sort of answers that eternal question of how do you get information about objects that you
Hmm,
cannot touch?
definitely.
And it turns out obtaining information from something that you can't touch or feel or hear, you can only see. Um, and it turns out there's a whole wealth of information there to obtain. And as you say, the Bohr model, it's not. technically correct, but at the time it was one of the best theories for what was going on, and that was in 1913. Not that long ago on the grand scheme of human history.
Right, right.
And the fact that we can still use it today to get a rough idea of what's going on is pretty impressive. And, it intuitively kind of makes sense. Um, and what we like to try to communicate to people is how light works, and how that leads in with the Bohr model is, it's as you say, it's a little bit simplistic. You have sort of fixed circular orbits, but if you think about an atom as something that's holding energy, and this is a fun one. I don't know if you've ever made this analogy. And again, this is not technically fully scientifically correct, but it's a thought experiment to kind of show how atoms or physical material might release light, which is electromagnetic, which is not matter. So
Hmm.
if you
Right.
have an atom that's full of electrons, shall we say, and those then get excited and release energy in the form of light. The way I like to kind of analogize it to some of my students when they're just starting out is, what if we filled up a balloon with air instead of filling up an atom with electrons? What happens to this balloon if I let out just a little bit of the air, and you get kind of that little squeak sound, so it's like squeak, and a little bit of the air puffs out, you get a squeaky sound, and the balloon is smaller, right?
Hmm. Right.
Um, and so you're releasing this little squeak of air at the cost of losing some air out of your balloon. And it's a little bit kind of like how and this is again just a little bit how we might think about these electrons releasing off light when the atom is getting excited. And if you're more advanced in your physics, I apologize for the analogy.
Yeah, definitely. Yeah, I must admit I hadn't thought of it like that. Although when I was at school and I found sort of electromagnetism quite and electronics sort of non-intuitive, and a friend of mine likened it to water in a pipe, and I think the voltage was a bit like the pressure that's driving the water around, and it kind of worked. It
Yeah, exactly,
gave me a sense of
exactly.
intuition for the subject.
Yeah, and it is very, very unintuitive. And that's why, of course, we have so many people over so many literal thousands of years taking a long time to agree on even what light is. Shall I take us back to a much earlier time than Bohr's model?
Sure.
Okay, so I'm going to go back in time a long way for
Right.
my next fun history item, because when we're talking about light and being able to get information out of light with spectra, and of course the simplest hydrogen spectra that was kind of working being Bohr's model in 1913, but a lot of people still think about Newton as one of the main kickstarters of the study of light as we know it. But I'm actually going to go back way, way, way further, because it turns out that the Romans knew about prisms and rainbows, and the amount of people over the number of years that have been looking at light as a study, as a science, it's worth mentioning because it's a tremendous effort of humanity to understand something that is really quite weird.
Mm.
When electricity and magnetism is very unintuitive, and light is electricity and magnetism. The Romans, as I say, they knew about prisms and rainbows. Euclid's Optics was written around about the year of 300 BC. So quite some time ago. And he studied vision. He studied vision and what is vision? How does vision work? and he created these things called the visual ray. And the idea is basically you have a ray gun shooting out of your eyeballs, and this luminous, and the quote is, this is a quote translated, luminous and ethereal emanation. So there's something coming out of your eyes, like lasers or maybe like sonar, like bats, that is allowing you to perceive the world around you. And the cool thing is, Euclid's optics is actually still really useful for ray tracing.
Right, right.
Um, so, and this is 300 BC, and it's obviously like we know that's not what's happening now, but this was the study of the time,
Hmm.
and bridging the gap between sort of the ancient Greek the studies of Euclid and Newton. We had a very prolific mathematician, astronomer, physicist of the Islamic Golden Age, which is Ibn al-Hazan, which is the Latinized version is al-Hazan. And this was around the year of 965, so not 1965, but
Hmm.
965
Right, right.
to 1040. And he was one of the biggest sort of revolutionaries, I would say, of of the study of vision, among many other accomplishments. And he was from the region where we have present-day Iraq. And now, this we're talking thousands of years, right? Thousands of years. All these people are working on it. And what we know today, of course, came from Newton kicking it off in a substantial way, but only after all these other people. And of course, we had before Newton, there was Kircher, Marcy, Boyle, Grimaldi, all these people publishing, working on optics. But Newton's optics book is still the one that really kicks it off, because this was due to his experiments from 1666 to 1672 using one of the main tools of optics today, which is prisms. And now I'm talking, things that are uh, um, less than 1,000 years ago. So 1666 to 1672, still quite a while ago. But this is roundabouts of 1,000, so 2,000 years later, and many, many, many different studies coming in. So the optics and the experiments, shall I say, of Newton's optics. If you get a copy of that book, it's really hard to read, and the notation is very strange. But the experiments, as described using prisms, if you translate them into modern English and modern mathematical formulas, you will get a feature of most undergraduate physics labs today. So, if you are taking your very first physics class, or if you're in grade school doing your first optics experiments, one of the very first ones they often start with is prisms. You hold this triangular piece of light up, or triangular piece of glass, sorry, up to the light, and
Right.
white light shines through it, and it's split into its constituent components. And the idea that light had components that you could split, that's where this revolution really came in. And once people got onto that idea, it really changed how we thought about light as a society. Now, I know I got to play with some prisms and lenses as an undergrad. Thomas, did you have any kind of Newtonian style experiments that were your favorites?
I guess we did some experiments with prisms, and I must admit I hadn't realised that they were effectively not really changed that much since Newton's time, and hadn't really. I mean, it's true that Newton was his optics experiments were probably as groundbreaking as his gravity, the universal law of gravitation that he's particularly known for. Um, but I remember the sort of classic experiment with a CD or DVD disc that if you hold it up in the light, it's got this really nice sort of iridescence that effect that the colors sort of seem to switch and flicker as you tilt the disc in the light. And it's a similar principle. I guess it's the grooves in the CD act like a diffraction grating, which is another way of separating out the the colors um in the light. And that the I guess the physics is the light path varies very slightly um as it reflects from the sort of adjacent grooves, that they're less than a millimeter apart. Quite a fine. Forget now the exact number on a. I guess a DVD is slightly higher density than a CD, but they're a few hundred I guess lines per millimeter. So that just right for the optical diffraction, and the sine wave kind of adjacent sine waves coming from each ridge, if you like, on the CD, then add or subtract according to the distance there. That if they travel a little bit more, there's a trough aligned with the next ray that's a peak, and then that would cancel. And the opposite is if they're both peaks as they align. I guess in your eye or a camera, then the color is added, so it strengthens. And that's a really great demonstration of the wave theory of light just from a CD.
Oh, absolutely. And of course, the wave theory of light is something that did not come about until much after Newton. In fact,
Right.
we have to wait for Maxwell in 1864. Remembering Newton was back in the 1660s. And they could see how the light was separating, but they didn't know that the light was behaving as a wave. So there was all kinds of really fun theories that people were coming up with to try to explain why certain colors of the light were moving more or less in the prism to make them separate. Because, of
Mm.
course, the glass
Right.
is different from air, and that difference uh, is different for all of the different wavelengths, which causes the white light to spread out into colors and make that pretty rainbow.
Right.
And of course, I always like to tell people if you're ever trying to explain this to just absolutely everyone, just grab yourself the Pink Floyd album art.
Right.
Because that rainbow being created through the prism is exactly what you need to start with.
Definitely. Perfect
Um,
example.
and of course, if you get, as you say, a couple more steps involved, you'll find that there are certain things, like as you say, the CDs, or if you're not using CDs, we'll call them coated silicon wafers. Because as I'm sure there are quite a lot of kids today who may maybe even have not seen a CD.
Bit antique, I guess, those
Yes.
old discs.
Yeah, and I do recall when they were trying to come up with alternative purposes, there were people making like handbags and clothes that had CDs on them because they're so cool and reflective.
Right, right.
It makes a really neat pattern. But it really is just silicon, which has been polished with some sort of coatings on it. And the coatings are, of course, what reflects the light at that different angles, that makes it create the pretty rainbows that we all know and love.
Hmm.
Now, we've got a bunch of other fun things we can discuss in history, but I think I might try to squeeze in just one more about the spectra before we move into kind of a news segment. So shall I get us into a little bit of stellar light analysis?
Hmm. Good idea, definitely.
Okay, so I actually think I might mix it up a little bit. I was going to talk about the first light from stars, but I want to actually just tell a little bit about what spectra is because we've kind of been talking around it. We've had a bit of history and what it isn't. It isn't quite Bohr's model. It's definitely not laser beams from your eyeballs, although it's a fun idea from a couple thousand years ago. But what we found out in 1864, or when I say we, I mean Maxwell's equations came together. And this is one of the best moments in all of physics because there were a lot of equations explaining how electricity and magnetism worked, and people came through these equations in painstaking detail to try to create some kind of explanation about what is electricity, what is magnetism? And these are things that they needed atomic models and physics to do. But in 1864, Maxwell put together several of the equations and found this jewel of physics by putting together known reactions from electricity and magnetism, explaining how those work. You could create an electromagnetic wave that would propagate by itself. No electron, no proton needed. It was just electricity and magnetism with no matter and literally nothing attached to it, flying through space by itself. It's pure energy by itself. And this was light, and it was oscillating. So what is light and what is spectra is a really interesting discussion that has taken thousands of years. Light is describing that electromagnetic radiation that has come together in 1864, and it has many, many names. It turns out that as your electric and magnetic fields wobble, the energy changes depending on how much they wobble per time. And this is where it gets, and I like to say, really, really weird because light is electromagnetic radiation by itself with no protons, no electrons, no atoms. It's been released from the atom or whatever it was attached to. And it turns out that as it travels through space, it bobs up and down in a wave pattern. So it's literally a wave, a sine wave. And the amount that it wobbles per time is that sine wave going up, down, up, down, up, down. If it's very, very wobbly, or basically bobbing up and down like crazy as it goes, this is a high energy electromagnetic radiation, high energy light, high energy wave. The highest energy is gamma rays. Then you get to a little bit lower to X-rays, and we've all heard of X-rays. They literally are so tiny and high energy they go through our body and bounce off our bones and create images for medical imaging. Ultraviolet is a little less familiar, but again, we're going a little bit slower. And finally, if our rays are going slow enough, we get visible light that our eyeballs can see. So your eyeball could get X-ray light, and I don't recommend it, or ultraviolet light, not good for your eyes. But those are so high energy, you can't actually see them. You can only see it when the light stops bobbing enough to be what's called in the visible range. Now, the visible light doesn't end there. If we go slower, if our light is going slower or wobbling slower, as I like to say, than visible light, we go into infrared. So if anyone's seen the movie Predator, any of them, they go infrared vision, heat vision. That is infrared light. It's like visible light, but slower. And our eyes can't see it, but it's still there. So we can build devices for it. We get slower than infrared. We go microwave, and then finally to radio, which is very, very, very slow. Very big, long waves that get, the size jumps over tall buildings in a single bound, basically. So light is going to be emitted in all of these different ranges or amounts of wobbling, and it will have different energies. So our radio waves are out there. They can be emitted by things in outer space, and they can be emitted by things here on Earth. So if we were doing a radio podcast, as we are right now, we could create them with transmitters on Earth and make radio waves. If we were in outer space, we could have our objects like our sun, Jupiter, or the center of the Milky Way, exciting neutron stars and pulsars. Anything that has charged particles undergoing acceleration could be a radio wave target. Um, so our light is going to be emitted for various reasons at different amounts of wobbliness or wavelength or energy, depending on how you like to write it. Um, and that is going to get us into spectra because in the 1800s, we finally had light being split out from astronomical objects. And there were, again, many, many experiments by many people that I couldn't possibly talk to you about all of them for, but lots of famous names like Fraunhofer, who in 1814 showed that when you look at the light of the sun, you create that rainbow of light out. It's not just a rainbow. It's a rainbow that has dark lines crossing it and some kind of bright lines actually too. So it's not a continuous band of colors when you look at the sun. And this was really interesting. So why is some light a continuous rainbow and other light is not? At the same time, people on Earth in the 1860s, Lady Margaret Huggins with her husband, Sir William, actually identified certain elements here on Earth that if I go and burn some sodium, it actually creates a bright line right there in energy or wavelength. And they were able to match some of these lines on Earth with some of the lines that had been found in the sun. So if I know what lines sodium creates on Earth, and I find those lines in the sun, then the sun has sodium. Game changer. So this always just gives me goosebumps when I think about it. So much fun. And then, of course, and then we really got cooking with astronomy, I like to say.
Right,
Um,
right.
so I think the spectrum of the sun is one of my all-time favorites of like that first solar spectrum with the lines in it from Fraunhofer. It just gives you goosebumps every time you see it because it's telling you what the sun is made of. Do you have a favorite spectra like that?
Um, I mean, it's true that the solar spectrum, I guess, is a classic, and with the new spectroscope that I'll probably talk a bit later, that you can get a really nice, interesting detail in the just by pointing it on a cloudy day that the reflected sunlight gives so much information. And when you were saying about these early experiments, Fraunhofer and William Huggins, it reminded me of a trip to the History of Science Museum in Oxford some years ago. That they've actually got, I think it's one of Sir William Huggins' spectrographs, that it has prisms, and it's it's kind of funny to look at because it's like a train of prisms, one after the other, to get increasing dispersion, I guess, as the light goes through and it spreads out. That one prism wasn't enough, and then they would have a darkened room and project the light onto a wall essentially to get the detail. And it's really amazing that and as you say, I mean, revolutionary really in terms of our understanding of the stars.
Absolutely. And on that note, let me just go ahead and take a quick reminder for everyone, because we're about halfway through the episode, approximately. Everyone, you are listening to York Universe, broadcasting live from the Allan Carswell Observatory, located at York University in Toronto, Ontario, Canada. Our website is yorku.ca/science/observatory for anything you want to find, really. as long as it's astronomy related. Tonight, you are listening to Dr. Elena Hyde and our special guest, Dr. Thomas Morris. We are talking about spectra and all kinds of really fun things. We're about to get into the news section. And to lead us into news, I want to send a little reminder to our listeners. This week, we will be having our regular Wednesday night free tour. If you would like to come out to see the telescopes, please keep in mind that we are alternating between observatory tours, which are inside in the domes, and atrium tours, which are outside on top of the Arboretum parking garage rooftop. So please check your tickets carefully to make sure you go to the right location. They are free, but we still do not want you to get lost, so bring your tickets with you. We are also running our Astronomer in Residence program again, which is open now. Our first astronomer is on the way up to Killarney Provincial Park. So if you would like to follow along with all of the adventures and imaging, please see the yorku.ca/science/observatory/air, AIR. You can follow along with the blog. If you're going to go out on site, it is a Bortle class dark sky preserve. I highly recommend it. And if you're looking to apply to be an astronomer in residence, please keep an eye out for applications for next year. They open roundabouts of February, and we assign all of our astronomers by the end of April. So, with that being the observatory news of the week, oh, and of course, as I think I mentioned before, in the intro, we do have a new all ages coloring book. So if you'd like to support the observatory, go ahead and have a look on that same website and see the store link for the new coloring book. All right, so we've been talking about light and spectra. What is spectra? What is light? And of course, getting into a little bit of prisms and gratings. Do you have any last thoughts you'd like to share on, I suppose, spectrograph technology before we get into the news, Thomas?
I guess I'll save up the piece about this new spectrograph I've been building. Perhaps till after the news item.
Oh, okay, wonderful. So do you want to discuss the little red dots first?
Hmm. Yeah, sure. Should we go to that
Okay, then
first?
let's go ahead and talk about the little red dots. So I always like to put a little bit of fun news in, and then of course we're going to have a pretty good spectrograph discussion after this as well. We've got really cool spectra coming in from James Webb Space Telescope, which should probably surprise not any of our regular listeners because James Webb Space Telescope is a regular feature of this program. We have a lot of JWST fans. In our hosts. But there's been a really big mystery happening out there in the universe, and we've been talking about how to get information from light. Well, the James Webb Space Telescope has an array of various different instruments on board, which basically help us to unpack the most that we can from the light that we get. Now, they're concentrated into the region of what we call infrared, which is a little bit different than some other telescopes you might have seen. Of course, it's just another wavelength of light, just another energy of light. But it's particularly good at finding things that are cooler and fainter and redder, which is very important when you go out past the Milky Way galaxy into the distant universe. And James Webb Space Telescope saw some really interesting things when they started looking at imaging in July of 2022. So there was something that they started calling little red dots. Almost every new image that they got originally, there were lots of things that they understood, stardust and gas and trails of light. But they had these little tiny, tiny, tiny red points, extremely compact, very bright, very, very red. And the James Webb Space Telescope started finding them all over, and we weren't sure what they were. Were they some kind of weird star, like really bright weird star, something kind of some kind of galaxy? It's too compact. Was it extremely redshifted? These little red dots were a mystery, and astronomers love mysteries. So the large number of these and the very, very extreme age, in fact, they think that they're so old, these little red dots might have been from a time when the universe was only about 600 million years old, which is very young for a universe. um, they seem to have been almost everywhere in the universe until about 1.5 billion years after the Big Bang. They mostly disappear. So we don't see them nearby to the Milky Way at all. You only see them in these very, very distant redshifted images. So they were pretty mysterious. And of course, when you have light that you're not sure about, what you want to do is, as Thomas was saying earlier, use more prisms to divide the light up more. So every prism that you use can divide that light up, spread it out more and more and more. The more you spread the light out, the more detail you're going to get for each little piece of wavelength, for each little line of emission that might be there, or absorption. So there was a lot of fun ideas. They could be some sort of super compact galaxies with bright black holes at their center. They could be kind of a never before seen stage of a black hole life cycle. But they think now that this is actually a totally new class of a cosmic object. So they think that they might be quasi-stars or black hole stars, which is an idea that was predicted 20 years ago and is super, super weird, but is gaining a lot of traction due to the new spectra that are coming off of these objects. And this idea is so strange. It's one of my favorites. It's basically the idea is something like this. You have a super, 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 super massive star, many hundreds of times bigger than our sun. And these things are so massive that the star is going to collapse under its own weight. It can't survive as a star. Gravity will win. And it collapses, and the center of it collapses so quickly that it creates a black hole. The outer part of the star is still there. And you basically have a black hole powered star. It's a sphere of highly heated plasma with a black hole in the middle. This quasi-star is such a crazy idea, but it would be very unstable, very, very unstable, because of course anything around that black hole would be close enough to be getting pulled in, and you would then just have black holes in the universe, which would not be emitting things by themselves. So that could explain why we don't see them today, and we do see them in the very, very early universe. It would also explain why they look so red instead of that big star blue that we're familiar with. And it's pretty fun. So thanks to the JWST spectra, we have a pretty cool idea for what these little red dots might be. And if you're interested, the spectra of JWST is from near spec prism, which is, we've been talking about prisms. And it looks at all kinds of different emission and absorption um, areas, and there's a bunch of different, you can actually find these online. If anyone wants to go see them, look for some of the notable little red dots. There's one that's called the Cliff, as in CLIFF. Very fun. This has a prominent what's called Balmer break, which is when there's a jump or a discontinuity in the spectra that you can actually measure. So the light kind of doesn't go smoothly up, it jumps at some point, and that's your Balmer break, which we probably don't have enough time to get into. So really fun news. Near spec prism spectra in the news this week for supporting some really interesting ideas around little red dots. Um, have you ever tried to look at any of the near spectra, Thomas?
Um, I've seen a few in some talks. I've not myself looked at the data, but I mean, they're tremendous. You know, to see these objects at redshifts, what 10, 12, or 14 even. They're way out there in, you know, in the very early universe. It's to be able to measure the the composition, the types of material that's there. It's really exciting, and I must admit I'd not heard of these kind of black hole stars. In It makes sense in the early universe, I guess. You've got such you know, the universe was much smaller than it is today, and the galaxies were sort of beginning to accumulate around sort of dark matter halos. I think my understanding in cosmology isn't, you know, I'm more of a stellar astronomer, but the sort of early universe was, there was a lot more material forming sort of more massive stars, sort of hundreds or thousands of times larger than the sun, and so it definitely seems, you know, that's could well be what we're looking at.
Yeah, it's a cool idea, and I do have to emphasize cool
Really
idea
is.
because
Mm.
we are still very much in process of figuring out what these are. But you're absolutely right. The early universe is a crazy place. You know, everything, and I do mean everything, was much closer together. And of course, if we're using spectra now, there are so many good targets we can go for, even if you can't get to the extremely tiny, faint magnitudes of James Webb Space Telescope.
Mm.
So I was thought it would be fun to focus next on some of your own you know, spectra and experiments, Thomas.
Sure, thanks. Yeah, in terms of the amateur astronomy community, there's kind of been a renaissance over the last 10, sort of maybe 20 years, of in terms of I guess the a combination of the camera, um, CCD, the charge coupled device, and then increasingly today with the CMOS digital camera sensors that have really allowed small telescopes to be used for quite exciting targets in astronomy that, you know, I guess when I was growing up would have been the preserve of professional observatories only. And so I've been involved with building a 3D printed spectrograph that's been developed by some French team of French astronomers led by a guy called Christian Brill, who's really you know, one of these optical experts that develops the spectrograph kind of in his backyard, as far as I can tell. I think he's an amateur astronomer, and but there was I think a conference about 15 or 20 years ago in France between the professionals who were looking at a class of active star, that hot stars known as BE stars. So the there's this spectral sequence that we've kind of alluded to with effectively a temperature series of the sun's kind of in the middle of like a regular mid sort of mid-class star known as a G star at about 5,800 Kelvin of its photosphere that we observe, and that's a kind of yellow, white yellow color. And as stars get hotter, they become white and then blue. So the B stars are blue stars, and they're kind of unstable. They're not quite as out there as these distant red dots. You know, they're kind of standard hot stars rather than anything particularly crazy. They're actually relatively rare in terms of the Milky Way, but we do see more of them in the sky because they're very bright, and so they tend to dominate over the far more common, but actually much fainter dwarf stars that are out there in large numbers, but don't really stand out to an amateur astronomers. And the BE stars are a special type of B star that has the E in the name is referring to emission lines where the gas is actually a lower density than normal in the star's atmosphere itself. And so rather than seeing an absorption line like you would with the sun, you see the hydrogen lines in particular are sort of peaks that stick up over the continuum, that the light for um, the of the spectrum, sort of broad shape of the rainbow is known as the continuum, and you have these obvious bright lines superimposed on it. And the stars are thought to be rapidly rotating, so they're actually 90% in maybe more, even more in some cases. We're not certain of their breakup speed. So they're like kind of flattened spinning tops that bulge out at the equator, and the wind and material seems to be sort of pushed outwards into a disk around the star, and they're really quite interesting to look at. And there's quite a few of them in terms of the stars that you can see with the naked eye. I think there's a Ashana, which is Alpha Eridani in the constellation in near Orion. So the brightest star in that constellation is actually a rapidly rotating star that I think it's a BE star. And there's plenty, sort of several hundred within reach of a small telescope, like an 8-inch, sorry, Schmidt-Cassegrain telescope that I have for spectroscopy. And so the 3D printed spectrograph is actually a really neat sort of accessible way into so-called professional amateur collaboration. So these scientific projects where amateurs can cover a lot of I guess the higher frequency observations in whenever the star is above the horizon, really, and if it's a clear night, rather than the professional telescopes tend to be much more focused on in high demand and only make a very a high quality but a very targeted observation that might miss some of the variability or the activity on these BE stars. And so that's something I'm really keen to get into with this 3D printed spectrograph. That it's a classical spectrograph design with a reflective diffraction grating in the end that sort of the light comes in at one angle and it's reflected off the grating, which is it's a high resolution grating, so it's about 2,400 lines per millimeter, and that means the profile of the spectral lines are quite spread out. So it's like a higher magnification sort of spectrum than you would normally see with say a prism, and so you can really focus in on these hydrogen lines and look at the shape that is changing, and it's quite different for different types of the BE stars. So each star basically is different, and it's a really interesting area, I think, to get into.
Oh, absolutely. Very fun.
Hmm, exactly.
Um,
All I need is lots more clear nights and get out to get some data.
Yeah, well, and this is great for any amateur astronomers who might be listening. If you are interested in joining in on something like this, there's a lot of wonderful targets like this that are pretty bright, that could probably use your small telescope should
Mhm.
you get those clear skies.
Right, right.
And it is getting easier to join some of these projects as well, I will say. With the of course the wonderful I'll just give a small plug for your wonderful handbook that recently came out. Um,
Thanks.
um, if you do happen to have the handbook, can they still get that online?
Yes, I think we have some printed copies available, and it's there's also a PDF download on our website.
Excellent. All right. Well, so yeah, if people want to follow in and grab that handbook, it's just on the main. Is it on the main page for the BAA?
I think it's under if you go to britastro.org, it's under a
Well, they'll be able to find it under britastro.org, which is great. And if you want to get the handbook, I can totally recommend it because it's really nice to have that printed copy in hand, even if you also have an online guide. Because if you're outside at night with your little red flashlight, I have to say there's nothing like a printed book to bring with you. There are some other observers handbooks out there as well as websites that can help you. I have collected a few of them on the page for the Allan Carswell website, which we've been plugging in this show. The BAA handbook is linked on our resources page, but you can go directly there as well as the RASC handbook, and of course things like Galaxy Zoo and some of the other online projects. We love to encourage amateurs to go out there and get all the observing you want to get and contribute to some of the science projects that are going on with your observations. And it's worth always noting that, like, some people think that perhaps, oh, my telescope is so small, or I'm in too much of a light polluted area. But that's, I think, why this target of yours is absolutely perfect because these bright stars are going to be relatively easy to see.
that yeah, that definitely the that's true. The hydrogen alpha line is relatively unaffected by sort of light pollution. I guess there are some bands of sort of water vapor and atmospheric material in that region, which again at the higher resolution, it's interesting. Not all of there's a sort of forest of lines really, so much detail, but some of it is Earth's atmosphere rather than from the target star. But the hydrogen
Yes.
alpha line is a
Yeah.
great and particularly in these types of stars, it's really prominent.
Yeah, and this is all what we were talking about before is getting the information out of the stars. Even if you're not up to maybe doing all the data analysis, if you get usable data out, there are places you can submit it where they'll help you with the data processing. And it's really wonderful to see that, as you say, with these stars, if you do get high enough resolution, you've spread the light out far enough that you can really see what's happening in these lines, you can tell things like the stars are rotating or the stars are, if they have winds, like some of these extremely strong wind stars we see, what kind of elements they have, what the temperature of the star is, how hot it is, what its color is. There's so much good stuff there. Now, we don't have a lot of time left for our show tonight, but I thought maybe we could quickly get you to tell us a little bit more about, since we've been talking, as you say, really cool projects that people can do. I know you have a little bit about this supernova project.
Yeah, that's right. So one of my colleagues in the British Astronomical Association, Robin Ledbetter, lives in the north of England. He's one of I would say, probably the leading um, amateur spectroscopist in the UK, and has been from his home observatory measuring a number of interesting sort of variable stars, sort of what Wolf Rayet stars, which are the really sort of extreme stars in the nearby universe.
Talk about winds.
Right, talking about winds exactly, and they're quite often in binary systems. But I wanted to talk about his one of his most recent projects was monitoring a supernova in the galaxy Messier 101. I think it's known as the Pinwheel Galaxy in Ursa Major. So it's a nice nice target for small telescopes in the Northern Hemisphere. And it's, I think, quite um, a, a active, an active galactic nucleus as such, but it's an active star-forming galaxy. It's a big spiral galaxy, I think, larger than the Milky Way, and actually quite often found that the supernovae surveys find supernovae, these exploding stars that get to the end of their lives and run out of nuclear fuel, and there's nothing essentially to support gravity in the star, so it collapses in on itself, and there's a core of the star quite often collapses into a black hole, and the outer layers get blown into space as the shock wave and the energy released in the core effectively escapes and drives the rest of the star apart. So the star unfortunately destroys itself. And one of these supernovae in 2023 occurred in Messier 101. And Robin actually observed it, I think, one day after its discovery, when it was still in the sort of the pre-explode, well, almost the shock wave was still just sort of escaping from the what used to be the star, if you like, and quite unusual to see a spectrum that soon after the explosion occurs.
Oh, yeah.
And he was able to monitor it for, I think, about 8 months, um, using a slightly different spectrograph than the one I've been talking about. That's a higher resolution. That for the supernova follow-up, it's actually much more useful to have a low resolution spectrograph, which means you see the whole of the color rainbow from blue light to red, and the the star is much brighter. Sorry, the spectrum is much brighter because you're looking at the whole of the light um, that's being emitted in the visible range rather than a very narrow fraction of light in the case of the higher resolution spectrograph. And he's actually been able to go down to about magnitude 18 with I think he's using an 11-inch Schmidt-Cassegrain telescope. So, not a sort of outrageously large instrument for amateur astronomers to be using. And he showed a really nice sort of plot of a sequence of the evolving spectrum from quite actually the early spectrum showed some really strong emission lines, and also the shape, of course, peaking in probably the ultraviolet due to the temperature of the supernova. I think they're sort of 100,000 or more Kelvin at the surface. Obviously, the core of the star is way hotter than that where all the nuclear reactions are occurring. But even the surface is hot, and it emits more ultraviolet light. So the sort of slope of the spectrum becomes flatter, and more of the light comes out in optical. And then you see at later times the hydrogen alpha dominates, of course, from the nebular sort of phase as the gas cools and becomes less dense, and you get a full sort of life of the supernova, which is really good fun to be able to track for an amateur.
Oh, yeah, absolutely. Now we're gonna have to wrap up the show here as we're just about at time, but I think this is a great place. We'll have to have you come back and talk more about some of these amazing targets because you've got, low resolution and high resolution targets, nice bright VE stars, and of course, the supernova is so much fun. And what you can do with amateur equipment now, if you want to, is really, really great. So any last comments on Spectra before we end off for this evening?
Um, I think I would just say, get involved and if you do make some observations, remember to send them in to the organisations like the British Astronomical Association and the American Association of Variable Star Observers. Both have an active spectroscopy sort of team that obviously your observations are much more valuable as part of a program or contributed to a database for future study.
Absolutely. And on that wonderful note, everyone, you have been listening to York Universe, the astronomy and astrophysics program written and presented by students, faculty, alumni, and friends of York University. The hosts this evening have been our special guest, Dr. Thomas Morris, and myself, Dr. Elena Hyde. If you are interested in the Allan Carswell Observatory, you can find all about our online programming, our in-person Wednesday night visits for free, and of course our new coloring book at yorku.ca/science/observatory. Thanks for tuning in to York Universe, everyone. Clear skies and have a good night.
Yep, happy observing.